The shipping industry is facing several environmental challenges. The focus is on treatment of ballast water, waste control, pollution to water, and emissions to air. Are there per se free solutions out there to reduce CO2 emissions? Let's focus on how the hull can influence fuel consumption and thereby environmental impact. In every vessel, there are some fixed factors given by hull design, propeller, and propulsion system.
Just a minor average improvement of hull condition can save the world fleet several billion US dollars per year, and few people seem to be aware of this.
When the vessel is at sea, there is a new set of factors: draft, trim, wind and current, fouling, speed, and voyage pattern. Some of these factors you can control, some you can't.
The smallest of elements that influence fuel consumption are the microorganisms. After only a few hours in seawater, surfaces become colonized by millions of bacteria. Other microorganisms attach and multiply, covering the surface in astronomical numbers. How does this fouling influence fuel consumption? Even a thin layer of slime can significantly increase bunker consumption.
Every ship has its own design curve, giving the ideal setting in service. When fouling increases the hull roughness, the vessel will experience a speed loss. To compensate for this speed loss, you have to add shaft power. This will dramatically increase fuel consumption. Typically, to compensate for 1% speed loss, the fuel consumption will increase with 3%.
If the average market speed loss could be reduced with 1%, the total fuel consumption would be reduced with approximately 12 million tons per year, reflecting a value of about 6 billion US dollars. You have two choices: lose your voyage days or increase the engine power.
For vessels in long-distance trade, true hydrolyzing anti-foulings has proven its advantage. Coating manufacturers claim that their own system is the best. The problem is, if you can't measure it, you can't manage it. Is coating vital? Let's see if you can measure it. A lot of ship data are already monitored. Readings from wind velocity and draft are easy to gather. RPM and the small bending or torsion on the shaft is monitored by the shaft torque meter. This device is typically installed for monitoring engine performance. On the other hand, the data are directly linked to propeller thrust. The Doppler log gives the actual speed through water. We typically discover the Doppler effect when we watch moving objects. Doppler radars are even used to measure wind shear on airports by measuring sound waves through air, and in our case, through water. Readings from these sensors are registered frequently. Traditionally, all readings from sensors on board a modern ship makes a complex matrix. The idea is to extract data linked to actual hull movement through water. When excluding data when wind velocity is over 6 bar and engine power is less than 50%, you've got the fair picture of speed through water and thereby hull performance.
The ability to monitor speed and power is vital for us. We recognize that fouling is a problem, and we are now trying high-quality Cylil antifouling in the hope of improved performance and less growth towards the end of the docking interval. Some vessels are owned, managed and chartered by different organizations. In our case, we handle all part of business, so my colleague handling the fuel bill and me responsible for fuel technology can easily meet over a cup of coffee.
The paint system consists of several parts, each vital for the performance. Cleaning, blasting and the different coating layers are factors we monitor carefully. The anti-corrosive must of course be taken care of, and regarding to antifoulings, the formula of the latest development is the icing on the cake.
Drag through water has been a major challenge in naval architecture, from the slimline tall ships to the vast cargo carriers. Today, every single factor counts, and resistance moving through water is essential.
Now we have monitored vessels with different anti-fouling systems, and we see a clear tendency that the extra cost of a true hydrolyzing anti-fouling is recouped through fuel savings within 9 to 18 months. If this small and virtually invisible factor is given proper attention, owners, management and charters can save big money.
We estimate that it should be achievable to reduce the average speed loss down from 5% to 3% with a true hydrolyzing anti-fouling. The reduction in CO2 emissions would give a significant reduction in carbon footprint on a global scale, in the range of 75 million tons per year. The challenge is getting those responsible for their specific budgets to interact. Maybe the charters should ask for a ship with this guarantee and be willing to pay more for it.
Regarding hull performance and fuel consumption, you now have the option to both measure it and manage it. Demand the benchmark anti-fouling system to ensure that every drop of fuel is accounted for.